How do modulation techniques synchronize receiver with transmitter? Imagine trying to have a conversation with someone across a noisy room. You need to be in sync to understand each other clearly. That's exactly what modulation techniques do in communication systems. They help the receiver and transmitter stay in perfect harmony so information flows smoothly. When signals are sent over long distances, they are changed or modulated by varying properties like amplitude, frequency, or phase of a carrier wave. But for the receiver to understand what was sent, it must match the timing and frequency of the transmitter's signal. This process is called synchronization. Synchronization involves two main parts: carrier synchronization and symbol or timing synchronization. Carrier synchronization is about matching the frequency and phase of the receiver's local oscillator to the incoming carrier signal. Without this, the receiver can't correctly interpret the message, leading to errors. To do this, systems often use phase-locked loops, which are circuits that automatically adjust the receiver's oscillator to match the incoming signal's phase and frequency. For digital signals like binary phase shift keying or quadrature phase shift keying, Costas loops are used. These loops not only align the phase but also correct frequency offsets and resolve phase ambiguities, making sure the demodulated signal matches the original. Symbol synchronization, also called timing recovery, makes sure the receiver samples the incoming signal at the right moments. Since information is stored in discrete symbols, sampling at the wrong time can cause errors. Techniques like early-late gate detectors analyze the signal to find the best sampling points, while maximum likelihood estimators use statistical methods to determine the optimal timing. Usually, systems first perform coarse synchronization to get close, then fine-tune the timing to eliminate small errors. Feedback mechanisms are constantly adjusting the receiver's parameters to keep up with changes, like movement or oscillator drift. In modulation schemes such as binary phase shift keying, quadrature phase shift keying, and quadrature amplitude modulation, synchronization is especially important. For example, quadrature phase shift keying uses for different phase states to encode to bits per symbol. If the receiver's phase reference drifts, it might mistake one phase for another, causing errors. Similarly, quadrature amplitude modulation combines amplitude and phase changes, requiring very precise synchronization to distinguish between closely spaced points on the constellation diagram. In systems that use time division multiplexing, where multiple signals share the same channel by taking turns, synchronization becomes even more critical. The receiver must know exactly when each signal starts and stops, which depends on tight timing alignment with the transmitter. This is essential in wireless networks like cellular systems, where signals can shift due to movement or environmental changes. It's also vital in broadcasting, ensuring that television and radio signals are decoded correctly. Even in control systems, where analog signals are modulated to reduce noise or allow multiplexing, synchronization guarantees commands are understood accurately. Special terms like constellation diagram help visualize the possible states of a modulated signal, showing how phase and amplitude relate. Matched filters are used to maximize the signal-to-noise ratio at the sampling points, aiding in timing recovery. Overall, modulation techniques provide structured variations in the carrier wave that the receiver can lock onto. By combining carrier and symbol synchronization methods, the receiver aligns its internal clocks and references with the transmitter, making sure the information is recovered accurately. This process keeps communication reliable across many electrical engineering applications, from analog control systems to high-speed digital data links.